Feedback amplifier. Feedback. What is feedback? The process of combining a fraction of the output energy back to the input is called a feedback. Output energy can be of any form, that is, it can be current or voltage. The process of combining a part of it or complete of it to the input again is called feedback. Why is feedback required? Feedback is used to control the voltage gain, the input impedance, the output impedance, bandwidth, etc. Therefore, feedback can be used to control these all factors. Thus, feedback is useful. There are basically two types of feedback. The two types of feedback are the positive feedback and the negative feedback. Positive feedback happens when the feedback voltage or the partial output voltage is applied to increase the input signal. The feedback is done in such a way that the partial output voltage is added to the input signal and it increases the magnitude of the input signal. This is called the positive feedback. Since positive feedback increases the magnitude of the input signal, therefore positive feedback causes excessive distortion and instability in the input signal. The second type of feedback is negative feedback. In negative feedback, when the feedback voltage is applied, it weakens the input signal. This negative feedback thus reduces the magnitude of the input voltage or current signal that is going into the amplifier or the component. This negative feedback thus reduces the amplifier gain, but it has an advantage such as it increases the gain stability. It also reduces distortion. If there is any distortion in the input signal, this negative feedback can be used to remove that distortion. It increases the input impedance and it decreases the output impedance to get a better output signal. The feedback network is given as in the following diagram. This is our output signal, that is, suppose V out. When it passes through a component of feedback that has a constant beta, the Vf or the V feedback is given as beta V out, where beta is a constant. Since this is a negative feedback amplifier, therefore the source voltage, the input voltage would be the source voltage minus the feedback voltage. Therefore, Vin would be Vs minus Vf, which on amplification gives us V out. So V out is equal to A V in, which can be also written as A Vs minus Vf. V out is equal to A Vs minus Vf. This negative feedback amplifier helps us to increase the gain stability of the input voltage. So V gain here is V out by Vs, where V out is given as A Vs minus Vf by Vs. Although the gain in negative feedback amplifier is less, but its stability is more. Voltage series feedback stands for when the output voltage is in series with the input voltage. So here we see that the Vs is the input voltage and there is a feedback here. So the A is equal to V out by Vin. A is the amplification. Amplification is given by V out by Vin. Voltage sample means the amount of voltage from the V output that is used for feedback. It is connected in parallel with the feedback circuit which has a feedback coefficient of beta. Beta gives us Vf by V out. Vf is the feedback output. Vf is equal to thus beta into V out. So beta is equal to Vf by V out. This is in negative. So it would go and get subtracted from Vs. Therefore, Vin would become Vs minus Vf. In voltage series feedback, the input impedance increases of the amplifier because the back signal returns to the input in series to oppose the applied voltage, thus causing the input current to fall and the impedance to rise. The second topology of feedback is known as the voltage shunt feedback. In voltage shunt feedback, the output voltage or the feedback voltage from the feedback circuit is connected in shunt with the input current. So here A is given as V out by I in, as the input is in current. Then it is connected in parallel with the feedback circuit. So here beta is given as, if the output is V out, then beta is equal to IF by V out, where IF is the feedback current, which is equal to beta V out. In the voltage shunt feedback, the I input shunt current drawn from the single source increases by amount equal to the feedback current IF, that as this is a positive feedback and the input impedance falls. The voltage feedback tends to reduce the output impedance in this case. Now we would be doing the third type of topology, that is the current series feedback. In current series feedback, we know that the output is always in current, and the series denotes that the input is always a voltage source. Since due to the presence of a feedback, the entire source cannot pass through the amplifier, therefore the amplifier can be given as A, the constant of the amplifier, is equal to I out. Since the current is the output is always in current, I out by V in. This is the amplifier where I out is the current. But in case of current series feedback, as in voltage feedback, we had done the sampling in parallel, but in current feedback, the sampling would be done in series. So a part of the output current is passed through beta, that is the feedback circuit, and since in series feedback the feedback voltage is connected in parallel in series with the input voltage, therefore the output would always be in voltage. So it would be Vf by I out. Okay, so what would be Vf? Vf, or the feedback voltage, would be equal to beta I out. This potential is our Vf. Since this is in negative feedback, therefore Vn would be equal to Vs minus Vf, or Vs minus beta I out. This is our input voltage for the amplifier. In current series feedback, the input impedance increases of the amplifier because the back signal returned to the input in series is opposes the applied voltage, that is the source voltage, causing the input current to fall and the impedance to rise. And in case of current feedbacks, the output impedance is always high. Therefore, we can write for current series feedback, it would have a high input impedance and a high output impedance also. In current shunt feedback, the output is always in current. That is the fourth type of topology is the current shunt feedback. In current shunt feedback, we know that the output must always be in current. Shunt means the feedback energy is provided in parallel to the source current. Since it is in shunt, therefore the source is always a current source. Therefore, since all entire source is not always passed through the amplifier, as a feedback energy is also provided to it. Suppose the current passing through the amplifier is I in, therefore amplifier constant or A is given as I out by I in. Here through the load resistance I in is flowing. As in current series feedback, we had seen that the sampling was done using the series connection. Therefore, similarly in current shunt feedback too, the sampling would be done in a series. So this is the sampling where a part of the output is passed through the feedback. Here, since it is in shunt, therefore the output will always be in current. Therefore, the feedback is given as IF by I out, where IF is the feedback current and is given by IF is equal to beta V out. In current shunt feedback, the input impedance falls because the current drawn from the signal source increases by the amount equal to the feedback current. That is, I input is equal to IS plus IF. Therefore, the current increases, and due to the increase in current, the input impedance falls. But in current feedback, we know that the output impedance is always high. Therefore, current feedback increases the output impedance. Therefore, in current shunt feedback, we have low input impedance and we have high output impedance. We are given a feedback network in which we have a source, we have an emitter, we have an amplifier which is in common emitter configuration, and we have a load. We also have a feedback connected to it which has a constant or a coefficient of beta. For an amplifier, now we are going to find out the gain when we have a feedback. In case of an amplifier, we know that if we provide an input signal, it amplifies the signal with a 180-degree phase shift. Due to this, it has a negative feedback, because when it is added to the input signal again, it reduces the magnitude of the input signal. So in case of amplifier, the beta or the resistive network is resistive and it does not provide a phase shift of its own. Therefore, the output signal or SO is given as A into SE, where A is the amplification constant. So it is A into SE. Since there is a feedback of SFB and it is a negative feedback, therefore it would be SI minus FB. SE is equal to SI minus FB. So we can write it as A into SI minus SFB, where SI is the input signal and SFB is the feedback signal. Since we know that SFB is equal to beta S naught, therefore we can write it as ASI minus A beta SFB is equal to S naught again. So we can write that S naught is equal to ASI minus A beta S naught, sending A beta S naught to the left hand side, we get S naught common. 1 minus A beta is equal to ASI. Therefore, since we know amplification is equal to gain is equal to output signal by input signal, therefore SO by SI is equal to A by 1 minus A beta. This is the gain for an amplifier using feedback. A by 1 minus A beta. Now we would be finding out the gain for a positive feedback. In an oscillator, as in the amplifier, we had seen that the feedback circuit was resistive, but in case of an oscillator, the feedback circuit has a frequency of its own. Therefore, what it does, that in case of common emitter amplifier, we had seen that it causes the phase shift of the input signal by 180 degree, but in case of but if there is another frequency or phase shifting component beta present, it further converts, adds 180 degree phase to the output signal. Thus, now the signal has a total phase shift of 360 degree, and thus it is in the same phase as the input signal. Therefore, it causes, when this feedback is added to the input signal, it causes an increase in the magnitude of the input signal. So we know SO, or the output signal, is equal to ASE, or we can write SO is equal to, since it is a positive feedback, therefore SE would be SI plus SFB, because SFB increases the magnitude of the input signal. Therefore, we can write it as A into SI plus SFB. Since SFB is equal to beta S naught, therefore we can write as ASI plus A beta S naught. Or taking A beta S naught to the left hand side, we can write as S naught 1 minus A beta is equal to ASI. Since the gain is given as output signal by input signal, therefore S naught by SI is equal to A by 1 minus A beta. This is in case of a positive feedback. For an oscillator has a condition that A beta is always equal to 1. A beta has a mod value 1. This is the Barkhausen criteria. Thus, the Barkhausen criteria states that the mod value of A beta is equal to 1. But as we had got in positive feedback, the gain is given as S naught by SI is equal to A by 1 minus A beta. If the value of A beta is equal to 1, therefore we would be getting A by 0, which is equal to undefined. Therefore, S naught or Si would have a value undefined. This happens only when the input signal or Si is equal to 0. Therefore, in case of oscillator, we can say that we would be getting an output signal although we don't have any input signal provided to it. This is the functioning of an oscillator. And it always satisfies the Barkhausen's criteria.